Right, good morning. As I said before, we will not take attendance today, but I will still give you guys some maybe short break in between so you can fresh up your mind before we cover the next topic. And I would like to start by discussing very briefly about your assignment number 1 that was released on Monday. So I wouldn't really get into the very technical details about how to implement a particular method. If you already started, you're having some trouble using Eclipse, or maybe you're having trouble implementing a method, you just have no clue, drop by my office hour. That you're more than welcome. Maybe on next Monday or Wednesday, after you guys have struggled a little bit with the problems there, you pretty much know maybe it's something you really want to get right but cannot really get right. I'll give you guys maybe some general hints. That's something I can do, maybe next week. Today, it will still be a little bit immature to talk about, like a dive into the method. But I want to remind you guys, you want to make sure while you're doing the methods, make sure you can also apply how to trace a recursion. We talked about in lecture number 1 and 2. Call stack maybe for simple cases, but you definitely want to see how you can use a tree to trace a recursion. I think that's going to lead you a very long way, even beyond this course. And also how to use a debugger. If you got any trouble setting up in Eclipse about a debugger, let me know. I think there might be some online resources for you to follow. Yes, question?
In a written test, would you specify to use call stack as opposed to?
Yes. If I ever ask you a question, let's say in the written test or the exam, if I say, okay, now trace the recursion, I'll be very explicit, whether you should use a call stack or maybe a tree structure. If I didn't say anything, you can use either.
Okay, so we should strive to get to know both, but if you have a preference for...
Yes, absolutely. So you should really know both and then be prepared to be asked either. Or both.
Do you have a date in your mind that the written test run, or is it easier?
Sorry, say it again.
Do you have a date for the written test run, or is it easier?
Do I? Oh, for the written test, you know what? Let's not get distracted for that. I'll communicate to you by writing today. Yeah, about a written test. Okay. All right. In terms of the help you can get on the assignments, my scheduled office hour is also always there. Just for today, so if you want to talk to me, please go for Zoom because I won't be on the campus in the afternoon. So please, Zoom me if you need to. And about the TA, I want to show you very quickly. So if you, as I mentioned when I walk you through about the syllabus, we do have TA for you. So if you go to the E-class, you will see I added one section there called TA contact. If you go there, we got 3 undergraduate TA. We got Qing Yi, we got Monica, we got Justin. So this is how it works. You can see the exact details also in this paragraph. Briefly, you can email the TA anytime you like, whenever you need help. There's no fixed tutorial hour by the TA, just to save time. So whenever you got a problem, you can send an email to the TA. The TA will try to respond to you at their earliest convenience, and then you guys can set up a time to go over your problem over Zoom. Of course, if a problem that cannot be solved, it will be directed to me again. And just make sure one principle here, anything related to grading, the TA does not talk about during their hour because they are not involved. These are more undergraduate TA. They are not involved in the grading. So later on, if you want to talk about grading ever, you need to speak to me directly, not email, okay? But try them out. I think they're all good TAs. They kind of know the subject pretty well. And if you want to discuss about some hints about solution, or even just want to ask about maybe for this particular case what I should do, things like that, talk to the TA. If you're not satisfied, talk to me too. Okay? I'll leave the choice to you. We'll provide everything that we could to you. That's about the TA. And then I want to just spend a few minutes showing to you some process. It's going to be also expected to be done by you in the programming test. Remember, you got 2 programming tests after the reading week. The way it's gonna work, it's not going to be from E-class, but similar. You have to somehow download your starter code somewhere. Let's say, for example, from E-class. Let's say if I click on this one here, the starter projects, it's actually going to be prompted to save somewhere, right? I already saved the starter project over here, right? It's called 2011 Windows 23 A1_starter.zip. That's an archive file you should really start with. Okay, I'll just show to you what you're supposed to do just to get you started. Launch the Eclipse, and presumably you created a folder maybe called 2011 workspace, right? It's a little bit small here, but for example, under my computer, I say under workspace, I got EECS2011. The name is completely up to you, okay? And then how do I import? So I'll show you quickly. Launch the workspace, and then the import does require certain steps you have to follow carefully. Otherwise, you'll be wasting time during the programming test. Right? You can either say import project over here, that's one option there, or you can say file and then import. Right? Under general, okay, you got existing projects into workspace. Click on that. And so there are two options over here. Do not choose the first one. Choose the second one. Select archive file. That's what you got to do. Archive file is a zip file. And you're going to browse. I'll show to you explicitly. Browse to where you save the archive file. In my case, desktop and over here. If you click on that, it will show you that there is a single project over there, 2011, Windows 23, and A1. That's the project you need to get started with. When you actually want to export for submission, you have to export the same project, but with a slightly different name, not starter anymore, all right, just to avoid confusion. If I say finish over here, sorry, the font size is a little bit small, but when you see the recording later, you will definitely see it's actually quite nice. Okay, under the source, we got empty model package. So anything you create need to go into this model package. Anything that's outside the model package you created is not going to be graded. Okay, it's got to be the model. It's set very clearly in the instruction. And under the tests package, there's one class there for the JUnit test. If you click on that, okay, so you can see here, you can read it through. The comments there says everything about what you should know, about the requirements, about the input and output. You know, remember how we define a computational problem. You got to specify the input and the output, right? You don't need to worry about putting Java doc. It's not required for this course, all right? And you got different tasks over here, but you can see you got some red cross over here on the tab and on the class over here. That means you got compilation error. Right? So you always gotta keep in mind, whenever you see any red cross in the Eclipse for your project, you gotta fix it right away. If you submit anything that has got compilation problem, you will get marked deduction. Okay? So when you want to practice this principle, which is good, you want to practice that when you're doing the assignment. Whenever you got a compilation error, fix it right away. And in this case, apparently you can see you're missing a class called recursive methods. I included some very short document in the assignment instruction there, so you can actually take a look to see how you can infer classes and methods from JUnit test. That's something you're supposed to do. And we assume you actually did something like that in 2030. All right? So catch up with that if you are losing their basics, but they're very straightforward. Just take some time to get used to. All right, you got 4 tasks to actually implement. I'll leave the implementation to you. And we can still try to run the test right away. You say, right-click on the JUnit test class, run as JUnit test. Okay, you can just say proceed. You can still run it. And what you will see is our report over here. It's telling you we got this many test cases over here, but you fell out of them, right? Bear in mind, these are just the starter test cases, and I put very explicitly in the instruction. When you actually submit this, let's say in the programming test context, you will be evaluated by some additional test cases, meaning that you should be very careful when you actually program. You don't want to program in a way that's only specific to the input values given to you. You want to make it general. All right? But for the assignment, it's the best chance for you to practice. Start with the starter test, make them pass, and then write some additional test cases for your method. And the understanding should be quite clear about what the method should do. If you got any doubts, reach out to us. I will try to clarify. Question? Do you have a question? Hello? You're fine, right? Okay. All right, so that's about running the test, and then, what about submitting? I'll show you very quickly. Okay, that's also very important. And everything I'm showing here, that's also set in the instruction, but showing to you might just save you some time. Let's say you're done with the project, of course, assuming that you got rid of the errors. Don't submit when you actually got errors in the project. Right-click on the project here that you want to submit. Rather than import, you will say export. Okay? And then under general, you will choose the second one, archive file, the zip file. And then you will say next over here. And so make sure you check the top level box, so it's going to include everything. We need everything from you, right? And it's got to be exported from Eclipse. So the grading script that we're going to use to grade your programming test assumes it's Eclipse. If you use any other IDE, then it will not be accepted, okay? And here you just want to choose some archive file name. For example, if I go to, let's say browse, go to desktop, I'm going to give a name. I think the name will be EECS2011 underscore W23 A1. Okay, so that's the name. And that's to be distinguished between A1 versus A1 starter, right? And if I say save, you will see that this path over here shows to you I'm going to save this zip file. And I say finish. And then you will see that this is what you were given to start with. This is what I just exported, right? You see the names are different. So don't get confused. When you, especially in your programming test, if you submitted the starter version, apparently none of the tests will actually pass. You have to make sure you submit this version here. Don't get it confused, all right? If you like, you can also try to export maybe this file for submission in another folder just to make sure it's different, all right? So that's the process and workflow I want to show to you. Any question? Anything that's not clear? Everyone's okay? All right. Okay. Awesome. All right, let me exit from the Eclipse. And meanwhile, you're going to do the work and see how you can deal with the recursion. I think these 4 tasks, the beginning ones are a little bit like a warm-up. You can definitely solve them with just a recursion basics lecture. But for the later one, you will definitely need to put into more thoughts. If you simply have no clue how to start with, drop by office hour or talk to the TA to get some idea. All right? Question? Yeah, so you can read the problem description more carefully. What you just asked about, what's going to be the format for the input string, is set very clearly over there. Please give a check. Okay? If you got further question, drop by, and then we can talk. All right? So next week, maybe I'll try to talk a little bit more about the methods themselves. We'll try to, if we have time. All right, if no further questions, let's now talk about some asymptotic analysis. Okay? This is where we were from last time. So we talk about if you got a general form of the runtime function, right? It's polynomial, going from the lowest power all the way to the highest power d. So we can guess it should be big O of n to the power of d, the highest power. It's almost always the correct guess. But to really prove it, you have to choose 2 things, if you guys remember, right? That's something we talked about last time. You got to choose the C, you got to choose the N0. And here is a strategy that will almost always work. So when I say almost always, you got to watch out if your runtime function contains any log. If it contains log, then sometimes it may not be exactly 1. So we'll see one example today. We'll get there. But this will be the C, the constant you have to choose, which will be the sum of the absolute value for all the multiplicative constant over here. And the multiplicative constant here may be negative. So that's why you want to make sure you change its sign by using absolute value. And also the N0 here will be almost always guaranteed to be 1. Right? I want to run a little bit proof together with you just to see how this can be justified. The proof itself is also a very nice way to review what you're supposed to do. And you just have to make sure the upper bound effects is always the case by choosing this C and N0. All right? Let's take a look. All right, so let's now take a look. That's the definition of the strategy. Oh, sorry, that's how you guess. This will be the strategy over here. And now we want to somehow prove the strategy. And the way to prove the strategy is you want to make sure the upper bound effects will start from N0 being equal to 1 and onwards. So 2 parts, starting from 1 and onwards. So 2 parts. Okay, let me sketch how we're going to do it, and then we're going to do it 2 parts over here in detail. All right, let's take a look. So we want to use these 2 to really justify, right? You want to say 2 parts. Part 1, and part 2. Part 1, you want to make sure the upper bound effects will happen at when n is equal to 1. You want to make sure f of 1, right? You can see I plug in n here to be 1, all right? Which should be less than or equal to the c that you choose, which is over here, right? I'm going to write it down in the actual proof, but I want to get it clear to you. And then what's g of n? This is g of n. All right, this guy here is g of n. All right, so that's why you got to put c times n to the power of d. And in this case, actually, the n will also be replaced by 1. Right? We replace every occurrence by 1. Every occurrence of n by 1. Right? So this one here is also replaced by just 1. This is what we are supposed to prove for the first one, for the first case. What about the second case? For the second case, you're going to just use a general n over here without replacing it by 1. So here we're going to put, let's see over here, let me use a different color. So you're going to say f of n will be less than or equal to c times n to the power of d. And of course, here we're assuming that n should be strictly larger than 1 because we have already talked about the case of 1. Right? Are we okay with the general plan for the proof? 2 parts we need to prove. Upper bound effect should be happening when n is equal to 1. That's what we're going to prove over here. Upper bound effect should be also the case for n larger than 1 and onwards. That should be this case over here. All right? Let's now do part 1. Okay? For part 1, let's try. Let me start with this side over here. Okay? F of 1. What is that? Let's plug it in. It's going to be A0 multiplied at 1 to the power of 0, right? You can see n is replaced by 1. Plus A1 multiplied n to the power, 1 to the power of 1. Plus all the way to AD, right? Multiplied by 1 to the power of d. Are we okay so far? All right? And one thing to note, there are 2 things we can do. First of all, you can see this part over here, this part over here, this part over here. I'll put it aside. 1 to the power of 0 should be equal to 1 to the power of 1 should be equal to all the way to 1 to the power of d. They will just be 1. That's obvious, right? Using some simple axiom or property of numbers. By using it, I'll put a star over here. And then we're going to simply factor out. And for this one, I'm going to put a star over here so you can refer to it. All right? And we're going to somehow, we want to lead towards this 1 to the power of d. So this will be equal to the 1 to the power of d. This is also equal to 1 to the power of d. Let's factor all of them out. So it will be A0 plus A1 plus all the way to AD multiplied by 1 to the power of d. Are we okay with this? Okay. Let me do a little bit of highlighting with this. This, and this, they are all equal. That's why we can do the factor out. All right. So now a question. Can we argue that this part over here is less than or equal to this one here? Absolutely, right? Because it's absolute value, right? For example, you can think about A0 less than or equal to absolute value of A0, A1 less than or equal to absolute value of A1, and etc. AD less than or equal to its absolute value. So we can say this one here less than or equal to. So this will be star star. Right? You can see star star over here. And that will be basically just A0 plus A1 plus all the way to AD multiplied by 1 to the power of d. Right? This part here, this part here is, let me do it again. This part here is how we started. This part here is how we ended, right? They're less than or equal to. So important to see that. Okay? Any question about the first part? Not difficult, but you have to watch out for the details, of course. All right? For completeness, why don't we do the second one as well? It will be done in a very similar way, but maybe by using a slightly different property for the number. But we'll see that. Yes, question? Okay, sure, no problem. Very good. Actually, I like your request. It's actually a very good point. Let's review the diagram. Let's say over here. How about this one here? Remember we talked about runtime function f of n over here, and this is the reference function that's modified with the c, right? What we just did for the first case is exactly when n0 is equal to 1, the starting point. We want to make sure, starting from that point, or at that point exactly, the upper bound effects is the case. And what we're going to do is to argue for n strictly larger than 1, the upper bound effect is going to maintain. It's not going to be caught up again by the runtime function. That's what we're doing. Case 1 and case 2. I like your question. I think that can also clarify. All right? 2 cases we're doing. You cannot miss any one of them. Let's go back to the proof over here. Okay, so what do we want to prove ultimately? F of n, where, okay, let's make a note over here. We're saying n should be strictly larger than 1. N strictly larger than 1. That's the side condition we have, right? We want to say f of n less than or equal to, this part here is the same, the c that we have chosen. And here will be n to the power of d, because n here is not 1 anymore. We're just using n in general. All right? Let's now do the proof quickly. So f of n will be, so here n will just stay as n. A0 multiplied by n to the power 0 plus a1 plus, oh, sorry, got to be careful. a1 multiplied by n to the power of 1 plus all the way to ad multiplied by n to the power of d. Okay? Let's just write it down first. What's our goal? Our goal is if what we did before, we somehow argue that these terms are pretty much similar or equal to 1 to the power of d. So that's why we can factor them out into 1 to the power of d. We want to do something similar, okay, in the following sense. We want to have n to the power of d. If somehow we can argue that these terms over here have some good relation with it, then we can factor that out. But what do we have? N to the power of 0, given that n is larger than 1. What can we say? n0 and n to the power of d. Are they equal or they're not equal? If they are not equal, how exactly should they be connected? That's really the essence to the proof. n0 here, and also n to the power, oh, sorry. N to the power of 0, n to the power of d. How do we put some relation between them, if not equal?
Consider that hopefully is less than or equal to if you replace all of the n to the i's with
Yeah, of course, you can do that. That's what we want to do. But I just want to argue individual components. All right? So for this one here, can you now argue that it's less than or equal to? It's guaranteed, right? May not be equal, but it must be less than or equal to. Also, n to the power of 1 also less than or equal to n to the power of d. All the way to n to the power of d, of course, less than or equal to itself. And let me call this star, star, star. All right? And then what we can do is we can now factor them out. But now you don't really put equal here anymore. You want to put less than or equal to. This is important. Okay? Star, 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 and then you're going to put a0 plus a1 plus all the way to ad, and multiply by n to the power of d, right? You can see the nd over here is the nd over here, right? We factored that out, okay? And we're getting very close from here to here. And we can use a similar idea as before. So this guy here is also guaranteed to be smaller than or equal to when you put all the multiplicative constant in the absolute value. Right? So this one here is just reusing again this part over here that we did before. Right? So what we got is A0 plus A1 plus all the way to AD multiplied by n to the power of d. Right? We started with this here, ended with this over here. And we argue about less than or equal to. That's important. All right? Well, the proof itself is not really that hard. You just need to apply the necessary properties. But I think as your classmate just asked, number one, you should really know what we are proving is, let's go back to this diagram. Let me emphasize once more. We are basically proving about N0 itself being 1, and also onwards. Both upper bound effect should really hold for both. And then we are proving that that strategy will really work. Okay, you should know the proof. Okay. Later on, when we get to, not too much proof we got to do for the linked list, but once we go to maybe trees, there will be certain many properties about the trees, especially binary tree, that we have to know their property. We're going to do a similar style of the reasoning. Of course, you got to make sure every step makes sense to you. So you will be able to derive by yourself, maybe in the exam. All right? Guys, any question? I'll take you. Just give me a moment. Let me just, okay, back. Yes, question. For written test, I can say most likely not. I think for the written test, we might focus more on the facts and or maybe some quick justification. For the exam, it's not unlikely. It's possible. Mm-hmm. May not be this proof per se, but maybe something similar, right? Yeah.
So I remember you mentioned before that like some students think that like if you have two nested loops, then it's n squared, but it may not always be the case. I'm one of the people who thinks like that. So are you?
Okay, good. No problem. So your name again? Abdul. Abdul was asking some question here, which is very nice. So what I said earlier was, if you actually got a nested loop in your method, it's not necessarily n squared all the time. Let me see if I got any example that I can go over today. If no, please maybe email me right before next Monday's class. I'll make sure I mention one to compare. Right? It's actually very important to know. You don't really want to make yourself a robot to see if I got triple nested loop, it's going to be n cubed. No, that's not the way. All right? We'll talk about it for sure. Alrighty, let's now move on. Okay, this one's done completely. And then, so this is a very important concept over here. And do you guys know what the symbol is? This guy here. Proper subset, not subset. All right, proper subset. Okay, let me explain that quickly, and then I'll show to you. Okay, this one is also very important to note. Okay, what we got is, okay, we got big O of n to the power of 0. A proper subset of big O of n to the power of 1. Proper subset of, let me do one more. Big O of n to the power of 2, and etc. Okay, what does that mean? That means, let me start with first of all, what's proper subset? Let's talk about it first. If I say S is a proper subset of T, all right, without bothering too much about the formal definition, it's going to distract the point. I'm going to visualize that for you and what you should really pay attention to. If I say this, that means I got a set S over here, and then I got set T. Okay, like that. S here and T over here. And two things you should know. Number one, each member in S is also a member in T. Because S is completely enclosed within T, right? Everything I can do, I can find within S is at the same time in T, right? The first point is rather straightforward, right? The second point is actually even more important. The second point is like this. There is at least one member of T that is not a member of S. Whenever you see if this is a formal relation between two sets or two families, for example, over here, that's the picture you want to think right away. And then these are the facts you want to consider right away, right? These are the two, all right? Guys, any questions so far? All right, having this in mind, let's now consider what's happening, for example, for this guy over here. And then the rest will be somehow very similar. You can derive from there. Let's try to draw the family for big O of n0. Let's say this is the big O of n0. And let's start with its very definition. Right? Do you guys remember the definition for the family of big O of n0? What's the definition? Intuitively. It's the collection of functions that can be constant. Oh no, I'm looking for the keyword. All the functions that can be upper by the n to the power 0, maybe with some constant. Right? Good. Yeah, I'm just trying to complete for you, but you're pretty much right. I'm pretty sure that's what you meant. Okay? The collection of functions that can be upper bounded by n to the power of 0. Right? Of course, by the way, n to the power 0 is equal to just 1, right? It's a constant. Let's see some example. Example would be 1 would be 5 and also 10 and etc. Any constant. So I might say f of n will just be equal to 1. F of n will be equal to 5. F of n will be equal to 10. That's the family of big O of n to the power 0. All right? And how do we visualize big O of n to the power of 1? It's going to be a superset, proper superset. You know, that's kind of the symmetric way to say proper subset. Okay? So here, this will be big O of n to the power of 1. Okay? Let's try to apply fact number 1 over here. How do we apply this to this scenario over here? We're saying that if these functions that can be upper bounded by n0, n to the power of 0, they can also be upper bounded by n to the power of 1. Agree? All right. Let's put it down. What can be upper bounded by n to the power of 0 can also be upper bounded by n to the power of 1. And of course, it's really referring to the purple one. All right? Okay, so far? How do we apply facts number 2 to over here? There is at least one function that can be upper bounded by n1, but it cannot be upper bounded by n0. Right? Can you give me one example? N, of course. 5n, 6n, 7n minus 2, and etc. Right? Let's put it here. There is at least one function that can be upper bounded by n to the power of 1, but not upper bounded by n to the power of 0. Right? You can see here, that's the purple, and this one here is the blue. Right? Let's make sure that's clear to everybody, right? I'm only talking about 2 sets over here. But the actual property tells you can go on for increasingly large power, okay? That means I can just draw another diagram for you. Think about n to the power of 0 is this little circle over here, this little family. And then we got n to the power of 1, and we got n to the power of 2. And usually the largest family you will normally encounter will be 2 to the power of n, which is exponential, right? That's just another diagram, right? Just show to you in the bigger context over here. And what's the consequence of this? Okay. By the way, guys, I think this one already explained, right? This slide here, right? Is already said. But look through the slides, just make sure you understand everything here. Another thing, which come a little bit later, I can talk about it right away. Given this, let me just copy this diagram here. I'll make a new page. Okay, that's kind of the family we have. Oh, I missed the N1. So family of N0, family of N1, family of N2, and family of N3.
The screen is not updated. The screen is not updated.
Oh, thank you. Okay, good. Thank you. Yeah, let's say this one here, right? Let's start from this. Let's try something that's correct, okay? Let's give one function over here. Let's say f of n is simply equal to 1. I'll give one example. Let's say system.out.println. Hello world. All right? That's a single line, which will be just 1. Agree? However, here you can say f of n is big O of n to the power of 0. That is correct. Is it also correct to say f of n is big O of 1? N to the power of, sorry, this is n, big O of n to the power of 1. Is this correct or not? It is, because this is also a member of this larger superset. Is it also correct to say the hello world program is also big O of n to the power of 2? That's also correct, right? I'm talking about correctness only, all right? Also, f of n is big O of n to the power of 2 all the way to f of n is also big O of 2 to the power of n. They're all correct. Let me finish this. Maybe that will answer you guys' question. Out of all the statements that's over here that's correct, there's only one that's the most accurate. You want to find the lowest upper bound that's actually valid, which will be this one here. This one here is what we call the most accurate upper bound. That's correct. Are we okay so far about this? For the hello world program, it can be upper bounded by constant. It can be upper bounded by linear. It can be upper bounded by quadratic. All the way to it can be upper bounded by exponential. That's the point I'm trying to make. And the follow-up point will be, why is this important to note that you should always only focus on the most accurate one? Why is that? I'll give you one example here, and then I'll take your question. Maybe that's what you're thinking. Okay. Let's see one example here. Let's say f1. Okay, let's say function 1. F of 1 of n is, let's say, 7n minus 2. Okay? Let's say we got another algorithm for solving the same problem, f2. That's 4n squared minus 3, let's say minus 3n plus 6. Okay? Let's say these are the two possible solutions to the same problem. And let's think about this. What if I'm not following the principle of giving you the most accurate upper bound? What if inaccurate upper bound is given? For example, I might say f of 1 of n is big O of n to the power of 3. First of all, is this correct? It is correct, absolutely, because this can easily be upper bounded by n to the power of 3. No problem. So that's correct. At the same time, I can also tell you f of 2 of n is big O of n to the power of 2. Is this correct? That's also correct, because n to the power of 2 corresponding to the highest power. That's the most accurate. I'm giving you inaccurate bound for f1. I'm giving you accurate bound for f2. And now, if you only take a look at this information without looking at this, which one would you choose? Oh, this guy here, which turned out to be actually not the most efficient one. So you can see how things can be misleading. That's my point. Whenever you give the upper bound, you should give the most accurate bound. Otherwise, you might just mislead the decision making. That's my point. Okay? And this part over here will be misleading for decision making. Right? These are all important properties you're supposed to know, and they are also practical for you to actually make your decision. Yeah, question? Oh yeah, you know what? That's a very good question. In other way, a more practical view from the instructor view, any student can say, oh, if you give me any algorithm, I'll just say big O of 2 to the power of n. Most likely, 99.9% of the time, it will be correct. But don't worry, I'm also smart, right? I will put in the exam, give me the most accurate upper bound. I will say that. If you don't give me the most accurate, no. Yeah. I didn't do that when I first taught this course. A student gave me 2 to the power of n throughout. I still gave them 0, but of course they petition. Yeah. But my point is, guys, we want to give accurate bounds, right? Even if I forgot to say that in the question, you still want to give the most accurate. Yeah. You don't want to tell everyone my algorithm is big O of 2 to the power of n. Nobody is going to care about what you did. It's too inefficient, right? All right. All right, hopefully everything is clear. I think for the basic stuff, you guys really deserve, very slow and very thorough discussion. Otherwise, you might just get lost for the rest of the course, okay? All right, so that's good. And I think, why don't we let you take maybe 3 minutes break? No attendance taking for today. Don't go away. And then we're going to do more example before the end of the class. Okay, take a break. Yes.
So we're saying that in that example, O to the n squared was more accurate than O to the n cubed, but because O to the n squared is less than O to the n cubed.
That's correct. That's correct. Yeah, you want to choose. Oh, how about you want to choose the smallest family that can upper bound your function? Yes.
And just kind of reviewing last week as well. When we're describing the upper bound, we're saying that's the worst case scenario for a program to take. Okay.
Yes. So we talk about worst case, but at the same time, when you talk about worst case, you got to give the most accurate characterization of your worst case.
Okay.
Very good. Yes.
Sorry, I took a brief look through the assignment. I was just wondering,
Yes.
Is there any grading on the efficiency of our solutions?
Not really. Good question. Not really for this course. How about this? As long as your bottom line, you got to terminate. You cannot run into infinite loop. But how about it? It cannot be too inefficient. What's going to happen is usually for the programming test, we set some a time limits on your method.
The unit test will fail.
Yeah.
Of course.
Usually we wouldn't give you a very large, 1 million elements.
We don't have to it doesn't have to be optimized.
No, you don't need to. But maybe out of personal interest, it might be your interest to optimize it, right?
Oh yeah, of course. But just to get full grades. I guess.
No worries. I can see your concern, but I can tell you sometimes the most intuitive or understanding solution may not be the most efficient one. So I'll leave that to you, right?
Well, the easiest is like a time constraint to just
time constraint.
get everything correct.
Yeah, everything correct, and then if let's say you got one solution that's running 1 second versus another one 2 seconds, to me there's no difference at this level. Yeah. All right. Good. All right, guys, another 1 minute, and then let's resume. 1 minute. Okay. Okay, we'll resume in just 1 moment. Yeah, we got about 24, 25 minutes-ish left, and we'll do as much as we can. And then we'll resume next Monday. All right, let's now resume, shall we? What we're going to do is 2 sets of examples I want to really complete today. We'll see at least a good part of it. In terms of the math example, let's do a few more for you to get more ideas quickly. So the one we did last time, let me remind you quickly, right? Given some mathematical function that represents the running time, this is what we did last time. We're gonna, number 1, guess what the asymptotic upper bound is, the most accurate. How about that? Now that you know the trick, don't just tell me it's 2 to the power of n always, right? Most accurate. And you want to prove it, right? Let's do a few more examples, just get you more comfortable, and then we should really try to apply this math into coding, right? That's really important. That's why we're doing all the foundation for you, so you can feel more comfortable and confident of doing that. All right, let's do maybe 1 or 2 more, and then the rest I can leave to you as exercises. This one here, number 2. Right? Number 1, we want to guess. Number 2, we want to prove. Okay? And of course, the question will be derive and prove the most accurate. All right? Asymptotic upper bound of the above function, right? More or less the wording you will see. And of course, as you learned just before the break, the most accurate. Okay, I of course misspelled that. Now, derive and prove, right? What about derive? Well, like a guess. Number 1 and number 2. Number 1 is big O of n cube, agree? Because if you look at the power, this will be to the power 3. This one here, 1 point something, right? As we said last time. This will be 0. So definitely, by all means, right? Big O of n to the power of 3. And we need to prove, right? I would say it's a no-brainer. Now that we have proven the strategy, you should really just try to add up the absolute value for the multiplicative constant and claim that it's n0. But verify just before you make sure you can leave to the next question. Okay? Let's see. Prove by choosing. By choosing. Okay, I'm going to choose, first of all, the C, the constant will be 20, 10, 5. Which will be 35, right? Yes?
Before log n, there's like obviously an invisible part. Maybe not add that when we are at the multiplicative constant.
What do you mean invisible? So this should be considered as 1 term.
Oh, okay.
Yeah, oh, this is multiplication, right? Yeah, there's no invisible. Not everything is visible here, right? Everything you should know is here. Yeah?
So I just meant log n is technically the same as 1 log n, even though there's no 1 there.
No, you don't really consider this a 1 here because remember, you should consider this is like n log n, and the multiplicative constant is 10. Yeah, I'm glad you raised it up. Maybe confusion for some others. Okay. All right, that's a C, and then the n0 should be 1. However, let's be safe. All right, let's be safe. verify. What we want to verify is f of 1 should be less than or equal to c times g of 1. That's what we want to verify. That's what you want to keep in mind. Let's do that. F of 1 is equal to 20 times 1 to the power 3 plus 10 times 1 times log 1 plus 5, which is 20 plus 0 plus 5, 25, right? Agree? All right. What about c times g of 1? C times g of 1 would be, we chose c to be 35. Multiplied by, what's g here? 1 to the power of 3, which will be 35. So now it's the upper bound effect over there. Indeed. Okay, good. So you can see it here. This is check. Because this is less than or equal to that. Awesome. Okay? Everyone clear what we're doing here? Guess, prove, and verify before you confirm to leave that answer for grading, let's say. All right? Do you need to show the verification part? Not really. I would say only if you verify but you failed. In that case, you have to change N0 to be something else. In that case, you must show the verification procedure. If you verify N0 simply 1, you don't have to. All right? Unless I tell you have to show every step, unless. Okay? It depends. All right, the next one. How about this one here? Also log. Question? Yes, go ahead. Good question. What if N0 failed? The principle will be, let's say N0 failed to be 1, you can try 2. If fails, try 3, and etc. Keep the C the same. Yeah, good. I will see one example very soon. Yeah. No, you don't need to. Somehow we already proved in some, or we don't really need mathematical induction. We already proved the strategy in that separate page. We assume it's really proved. So when you apply it, you can just do it. That's okay. Yeah. So when you verify, you don't really have to verify for many cases. Just verify for N0 being 1. Yes, exactly. You want to make sure that also works for this particular example over here. Yes. All right, next one. All right, let's do it together. Okay, and the problem you will be given will be similar, right? I'm not going to repeat. This will be the problem you'll be given, right? Okay, number 1. What's the asymptotic upper bound? Well, what is the highest power? Basically, you want to decide between log n, right? Because let's say we drop this, right? And this one here, think of it as equivalent to 3 times log n plus 2 times n to the power of 0. You want to decide whether 0 is higher or log n is higher. Okay? Log n is higher. That's something we said before. Constant is always the lowest. Nothing can be lower than constant. All right? So the highest power should be log n. All right? And how do we prove it? Prove by choosing, let's write it down, just by applying the strategy. By choosing C should be multiplicative constant 3 and 2. 3 plus 2, which is 5. And 0 should be 1 in general, but let's verify. All right? For those of you who can calculate in your mind, you might find that this one may not be verified, right? Let's see why. Okay? Again, what do we want to verify? Let's remind ourselves. F of 1 should be less than or equal to C times G of 1. Okay? That's something we want to do. Now, F of 1 will be 3 times log 1 plus 2. Right? I just plug in n here just by 1. Which will be, what is that? 5? 2, right? Okay, I'm checking. Just make sure, right? 2. Right? Because 0. All right. What about C times G of 1? C times G of 1 will be, C will be 5 times G of 1. G of 1 will be, G is here, right? That will be log 1, which is 0. Is 2 less than or equal to 0? No. That's the case where verification might fail. And for your information, I tend to like this more on the exam because I require you to write more. I'm already giving you a hint, but not necessarily the case. It's like a reverse psychology, right? You thought I will give you this one, I might give you the simpler one. So you got to get prepared for both. Okay, that's my point. All right, and what should we do? As you mentioned before, okay, I'll tell you what you should do, and the rest will be exercise for you. Okay, this failed. Because this one here failed. It's not the case, right? So what we should do is keep the same C. But for N0, increase it to 2 to see if that works. All right, exercise for you. If that works, you can stop. If it doesn't work, you got to go on to the next one. All right, is it clear about how things should be done? Don't make any pre-assumption. It may fail, it may succeed. Just go with the logic. Go with what you're supposed to do. Right? With the kind of visualization we did last time, I think the diagram there, I think it should really make sure you understand it by heart. That will really help when you do all the reasoning. Okay, I've got about 23 minutes-ish. I think I'm right? What we should do is we should do more example. And this one here, quickly, okay? And then we're going to see how to apply this to code. You can do a little bit of rewriting here, 2 to the power of n plus 2. We want to somehow get rid of the multiplicative constant. You don't really want to say big O of 2n plus 2. This is not good. Because we want to drop all the multiplicative constant and lower terms in the big O, as I said before. Rewrite this as 2 to the power of n times 2 to the power of 2, right? Easy math. 4 times 2 to the power of n. You can drop it. Agree? So it should be big O of 2 to the power of n. That should be the answer. All right. I presume everybody's okay with this. Rather easy. It just shows to you you have to somehow do a little bit of massaging on the term to make sure you can drop the lower term and the multiplicative constant. Number 5. What about exercise for you? All right, I think you guys should really do a little bit of exercise. Okay, exercise. I think as for the math, we have done enough. Explanation and also example. I think you guys are ready to apply this foundation to code. That's really the whole spirit of this course. You learn about theory, now apply that to coding. All right, let's go with that. We got about 22 minutes-ish. Oh, before that, let me make a little bit concluding remark for this part, and then we will be ready. Okay, let's take a look. All right, so everything we have said already, and as closely as possible, most accurate, right? Something we'll also talk about before the break. And classes of function. I think this will be some very important table for you to know. We kind of mentioned that also earlier, right? We talk about polynomial over here, right? And I want to talk about this diagram very quickly. Okay, you can see this diagram here kind of lists to you, starting from the cheapest one, that's constant. Let's take a look. This is the constant. Let me try to use a highlighter. Okay, constant is over here, flat. Think about what constant function really means in this plot. We're saying that n here is the horizontal axis. As the input size grows, constant remains constant for the running time. It doesn't change. This will be the most ideal scenario for your algorithm, given that it's correct, right? Correctness is so important. If it's not correct, it doesn't matter. All right? On the other hand, let's take another one, for example. If you got another function, let's say that's linear, well, even n log n, let's say. N log n is the more expensive one, compared with constant. If you look at that, I believe that one's here. Okay, this one here. This one here, apparently you can see there is always a gap between n log n and also the constant, right? So that means if for solving the same problem, given that both solutions are correct, if you have one constant here and one n log n over here, by all means, choose this one, the green one, because the running time is just going to be so efficient, even as the input goes towards infinity, right? That's how you should really interpret this graph. Try to look into other functions as well to see how they actually grow. Of course, this one is really the nightmare you have. You never want to have a 2 to the power of n, all right? This one here. Yeah, give me a moment. I'll write some remark and I'll take your question. This one is never try to write an algorithm with this running time, right? Of course, sometimes maybe that's the only solution you have, but I'm just saying that should be the worst case you can expect.
I know in theory it's possible to have like an algorithm that's like go to the n factorial, but like
n factorial, let's not worry about factorial just yet, but factorial itself is also like a polynomial, right? If you say, well, think about it, n factorial itself would be n multiplied by, n multiplied by n minus 1, etc. So it's still polynomial, but don't need to worry for now. Yeah.
I was just thinking like that would be the first one, so I'm not sure if it's like possible to be done in like Java. Maybe
I don't have any example for that on top of my head. Maybe as we move on with the course, follow up with me again, and then we'll see if there is any example. Yes. Question? You okay? Yes, yes. Good question. So when you say 2 to the power of n versus 3 to the power of n, they are the same thing, really. Big O-wise, they are both in the family of 2 to the power of n. You can easily write this one here. Here it would be 2 to the power of something and then 2 to the power of n. You can think about 2 to the power of something will be equal to 3, and then to the power of n. So you can still rewrite it as 2 to the power of n. That's a quick justification. Yeah. So they belong to the same category. Asymptotically, they're the same. Yeah. Okay, good. All right, so I believe that might be the last one I want to talk about. Yeah, that's good. Okay, let's see anything else on the slides, and then we'll do example. Good. So now we want to do a series of examples to show to you how you can apply the math to the coding. Let's start with something simple. Take a look at the code first to know what it is doing. But actually, when you are asked to derive the asymptotic upper bound, you don't really have to know exactly what it is doing. You can be more like a robot just to analyze the structure of the code. But you can take a look to see what it is doing. It's doing something you should know. Right? We're just doing maximum of, right? Just max. Okay? A general principle you can assume. When we say if you got a loop, it's not necessarily linear. If you got a double nested loop, it's not necessarily quadratic. On the other hand, if you don't have any loop, most likely it's constant. I don't think there's any exception. All right? If there's no loop, you can safely assume the algorithm is simply constant. All right? Yes. Recursion is in some way like a loop. Let's not worry too much about recursion. The way we're going to derive the running time for recursion will be a little bit different. Let's not worry. Yeah. Mm-hmm. Now we assume no recursion, right? Leave the fun for recursion to your assignment 1, not here. Okay? Don't worry. Okay? All right, for this one here, any guess what the asymptotic upper bound should be? Farads? Big of 1. Yes, let's see why. So now, you're not really asked to calculate the precise number of primitive operations. Right? Let me do a little bit differently. Right? Of course, if I ask you to really count exactly how many primitive operations there are, You got to do it differently, right? Like what we did before. I can still judge line by line. This one over here, just about assignments, I'll put 1. This one just about comparison, also 1. This one just assignment, I can put 1. This one here, just return, also 1. Basically, if it's even more than 1 primitive operation, I'll still put 1. Just telling me that it's just constant. And overall, I'll just put big O of combining them all together. 1 plus 1 plus 1 plus 1. 4. You can think about, it's just big O of 1. That will be the final answer. This one here is not even correct. This one you should think about, it's more like it's like a 4 times n to the power of 0. So you want to drop the 4. So you only got n to the power of 0 left, which is 1. All right? The final answer should be this. Not this and not this. That might be the intermediate work you want to show. All right? Yes?
The if statement could evaluate to false. So when we are counting pairs, do we just...
No, we don't consider. Yeah. So when you derive the running time, when you try to approximate the running time, you don't consider the logic of the program. Even if you got the so-called dead code, like some branch you will never write into, that's okay. We don't worry. We talk about worst case, which sometimes might be overly pessimistic, but that's okay. Okay. All right, the first one. Let's do the second one. How about this one? Oh, this is something you know, right, from before, find max. But let me now do this same example here with a little bit quicker derivation, rather than counting very precisely. How would I do it? Roughly speaking, you can see line number 2, just 1. I have an indexing, I have some assignment, just 1, constant. Okay, so this one here. And for this one here, it's a for loop. So I know that this is going to be evaluated somehow, some number close to n. I don't need to worry about whether it should be n, n minus 1, n minus 2 precisely. I don't need to for approximation. So and this will be some constant as well. So I just put n. For this one here, just for this line here, right? This one over here will be just 1 by itself, just for the body of the loop. Okay? How about this? Let me put this one here. This part here will be the body of the loop. I'll show to you why I'm writing this way. That might be easier for you to consider. So this will be the body of the loop. For each iteration, this line here will just be 1, right? And this line here will also be just 1. This one here is also 1. And this is outside the loop, which is also 1. Now, how do I combine them? Big O of line number 2 is 1 plus this header over here and also this evaluation here, overall will just be n. Plus, how many times are we going to execute the body of the loop? Approximately n times. All right? It's going to be n multiplied by, inside the body of the loop, 1, 1, and 1. 1 plus 1 plus 1. And then outside the loop, we got 1 here. Okay, I'll annotate it quickly. The 1 here is really referring to line number 2. The n here is really referring to the header of the loop. The n over here is the number of iterations. The 1 plus 1 over here is each iteration. And the 1 here is the final return. And you don't even need to show exactly what this is. If you want to, brilliant. But if you don't want to, you can see the following. 1 here, n here, also n here as well, right? It's just some constant. What will be the highest power overall? N, right? But if you don't really feel safe in thinking this way, sometimes you might miss. So I would suggest you can still try to evaluate exactly what this is and then put the final answer here. But if you want to do it this way directly, that's okay. But we want to see some intermediate work to see what's really here. All right, so that's the final answer. Question?
Instead it was 2 plus n plus 1 is like an approximation, right?
Approximation, yes. So what we're doing here is only approximation. So it's okay to be one off, one more, one less, doesn't matter. I can tell you this. You can do any approximation you like as long as it does not impact the highest power in your final answer. Because if you got the highest power wrong, you get a final asymptotic upper bound wrong. That's the principle. All right? Yes. Yes. Yeah, absolutely. So this one here, I'm just trying to show to you guys for the first time. You can feel free to also put 1. But I would say it will be safer if you put 1 plus 1 plus 1 here. Because potentially there might be another loop. Right? In which case, it might be nicer for you to separate. Yeah. I'll leave the choice to you. Okay? Alrighty. Next one. This one here, let me see, 3 here, 4 here, and 5 over here. Why don't we make sure we finish 3 and 4? Number 5 is a bit trickier. Okay? We'll see if we can do number 5, give you a little bit hints, but at least do 3 and 4. Okay? How about 3 and 4? Let's start with some, why don't you take a look first? And if you guys just give me some idea, if you remember what I said before, even if you got nested loop, doesn't really mean it's going to be n to the power of 2. It may be, or it may be not. Depends. Okay, what's your guys' guess? Just tell me the answer directly. N, okay? N squared, N, okay, good. You know, just before I forget, and here you go, that's what you wanted, right, as an example, okay? I'll give you one example. Think about why. I'll talk about this one in a moment, but as I promised to your classmate, I'm going to give one example, different example to show him. Okay, I'll give you 2. How about that? And that's something I will rely on you to think about, okay? Let me make some slight modification. If I modify this guy over here rather than n, if I say 10,000, the answer would be big O of n. If I modify this and this, let's say 1 million, even 1 billion. I'm exaggerating it just to show to you the point. We talk about asymptotic, all right? It will be big O of 1. The essence of these 2 extra examples is you want to think about what you're putting as the bound of the loop. Here, here, and here. They're all considered as constant, regardless of how large they might be. They're just constants. Right? I'm going to go back to the original problem there, but you guys think about why. This will be this, and this will be this. So hopefully that gives you a little bit tricky thing to think about, right? Think about it, and come back to me later. Think about it. Okay, let me go back. That's the original problem. So the bound over here is n and n. Okay? I would suggest if you actually got a nested loop, you may just want to try analyzing the inner to the outer. I think that'll be a better strategy. Sometimes it may not be, but I'll say usually try with this first. So let's say this. This part over here, let me use highlighter. This part over here, this one here, and also this one over here, and also this one over here. This will be the body of the inner loop. Let's try with these guys, right? Approximately, what will be the number of primitive operation here? Approximately 1. Okay, very good. You can see no loop in this part here. Try to isolate what you're considering. Very good. Okay, I'll put 1 here. Okay, and this guy over here is simply just an extra body, right? This is also 1. All right. And now what you got to think about is, let's do a little bit pattern over here, okay? Here, so guys, please hang on there, okay? I know you guys are excited about this kind of a challenge here. Please. Right, so I would suggest let's try to do something formal, a little bit more formal. Look at the header here. To figure out exactly how many iterations you might have, I would suggest let's try to enumerate or see the pattern of the loop counter. This will be so important because we're going to see a slightly more challenging exercise, and I'll do that maybe on Monday to start you with. Right? For that one, they definitely want to see the pattern to justify. But for this one, let's see. We want to see the pattern. Okay? What's the pattern of the loop counter? Okay? And to really see the pattern of the loop counter, you're going to go from outer to inner. Start with I. I is going to be from 0 all the way to n minus 1. Let's not worry about n, which will make it false. Let's not worry. Okay? We'll talk about iteration. Okay? So for I, it's going to go from 0, 1, 2, all the way to n minus 1. Are we okay with that? That means the outer loop is actually going to the outer loop runs for n times. And something might be trivial to you, but I really need to mention explicitly. How do I know it's actually n times from 0 to n minus 1? Right? Do you guys recognize this notation from math course? If I got lower bound A, upper bound B, and if I put square bracket, that means they are inclusive on both ends, right? And if I'm given arbitrary A and B, assuming that A is smaller than or equal to B, how many numbers are there in this range? B plus 1? No, because A here may be any number. B also be any number.
Oh, B is included in the range. So.
I'll write it down. B minus A plus 1. For example, if I got 0 to n minus 1, that would be n minus 1, the beginning, minus 0 plus 1, which will be n. All right? It's a nice formula to know about. If you're having trouble understanding this, speak to me. More than happy to give you more example. But that's important. All right? That's how I figure out n times over here. All right? And there are two dimensions. First dimension is about I. Second dimension is about j. So let's talk about j. For every I value over there, there's going to be some value for j. Let's see. Let's say when I is equal to 0, and we'll go into execute this for loop, that's inner, right? The inner for loop. What will be the value for j? So that means I'm going to figure out for I is equal to 0, what should be the corresponding for j? Only 0? Are you sure? Or more than that? Doesn't that go from 0 up to n minus 1? Guys, agree? Okay, maybe you missed that part, okay? It's going to go from 0, 1, 2, all the way to n minus 1. Are we okay with that so far? What if we go to the second iteration for the outer for loop? Now I will be 1. How many value for j? Same, because this is always bounded by n. And the starting value is always 0, but may not be. All right, we'll see one example where it's trickier. Okay, so this one here will be 0, 1, 2, all the way to n minus 1. The pattern goes on even for the very last iteration where I is equal to n minus 1. What about j? The same, right? 0, 1, 2, all the way to n minus 1. So this pattern here tells us very precisely how many iterations there that's going to execute the body over here. Okay? So now you can think about for each iteration of I, we actually got, let me try to maybe put this part here. You can see this one here. In a loop runs for also n times. Okay, so we got two critical number here and here. Oh, let me finish this and I'll take a question. Yeah. So what we want to say is, for every single iteration of j, for example, let's say here, we're going to execute this body over here once. Once, 2, 3, 4, all the way to n minus 1 when I is equal to 0. 1, 2, 3, another n times for when I is equal to 1. How many times are we going to execute the body over here? Let me put down the observation here. For each iteration, I will finish this one example only. Okay? For each iteration of the outer loop, we will execute the inner loop also n times. You know what? How about this? Let me just stop over here. I do need about 5 minutes. I don't want to drag you guys over time too much. I would say here, up to here, make sure you understand what we're doing here, and then I will try to conclude from here. To be continued on Monday. But guys, make sure you really understand what's really happening over here. You will need something like this for a trickier example. All right? See you next week. Commute safe. Yes?